We've seen a general view of duality. Now we're going to specialize even more to linear programming and also enjoy the fact that, see the fact that linear programs always enjoy strong duality, unless the primal or dual is infeasible, then or one of them is unbounded, then they enjoy strong duality. And this is not true for general convex optimization problems. Now let's so why don't we start again by looking at the standard form linear program. So minimize C transpose X subject to AX equals B, X greater than or equal to 0. We know again that we've seen in previous lectures that we can bring any linear program into this format. So we might as well just look at this. And again, using this min-max or max-min approach and flipping the min and max, I guess let me write it this way, the min-max to max-min approach, we can derive at least the form of the dual. You've already done a more general exercise, or I asked you to do a more general exercise in the previous lecture, but you might as well do this now to get some practice, and you'll find that this is maximize P transpose B subject to P transpose A less than C, and P in this case is free. Some repetition always helps. It just especially when we get into combinatorial problems, being used to thinking about what the general form of the dual is and how we go from primal to dual is going to be helpful. Even though at the end of the day these are more or less simple algebraic manipulations. Okay, so what does weak duality tell us, or what does this min-max flipping to max-min tell us? It tells us that this min is less than or equal to this max. So in particular, let me clarify here even more. It's saying that, so what weak duality says, and we do not need anything, no linearity, no strong convexity to make this claim. It's really just immediate. That for any feasible X, and I mean primal feasible, and for any dual feasible P, C transpose X, pardon me, this is reversed here. Again, it's reversed because the maximizer is hurt when the maximizer has to go first. That's why min-max is always going to be bigger than max-min. But weak duality tells us that for any feasible X and any dual feasible P, C transpose X is going to be greater than or equal to P transpose B. And this is by itself already useful. Strong duality tells us that if you choose the best X and the best P, X is pushing down, P is pushing up, that there's going to be no gap. That's what strong duality is telling us. So we're in standard form, so let's try to take advantage of that. Let me make a little bit of space for myself on this slide. Actually, let's just have plenty of space on this slide. Okay, so again, I've got minimize C transpose X subject to AX equals B, X non-negative. This is also where we start our simplex method. So simplex method goes from basic feasible solution to basic feasible solution. BFS, basic feasible solution. Remember, this is something of the form X is equal to X, B, 0, where X, B is equal to the columns of B, of A, AB inverse B, where B is a subset of the indices 1 through n of size m. And what does a simplex method, let's recall very, very quickly here, what does the simplex algorithm do? It keeps updating. And in here we've got xb, which is equal to a b inverse times b. That's what's sitting here. And these are always non-negative because simplex algorithm goes from basic feasible solution to basic feasible solution. Go back and think about the simplex algorithm, and you can see that the pivot rule is exactly designed in order to maintain primal feasibility at all times. So the way that we choose how far we can move is exactly given by looking at the ratios. We won't go over all that. And when do we stop? We stop when what sits here is non-negative. So these are the reduced costs. And let me remind you what those are. So the reduced costs are C bar. And these are defined as C minus CB transpose AB inverse A. We already know that for any I in the basis B, C bar I is equal to 0. And simplex algorithm keeps looking over the reduced costs until it finds one that's negative. And when it finds one that's negative, it introduces that into the basis. And when you move theta units in that direction that you get by introducing that element in the basis, your benefit is your reduction of the cost is theta times the reduced cost. Therefore, as we already saw, a particular BFS X is optimal exactly when, if and only if, C bar is greater than or equal to 0. So note again one subtlety that could happen with degeneracy. A basic feasible solution, I didn't say the geometric point, because for a geometric corner point, this does not exactly hold. It's not actually clear what this means because in the presence of degeneracy, the geometric corner point could actually correspond to many different bases, and therefore many different basic feasible solutions might actually be that same corner point. But a basic feasible solution is optimal if and only if C bar is greater than or equal to 0. Let's rewrite that looking at this expression, and let's call this P. Now, for obvious reasons, you'll see that this is actually going to be the dual variable, but what this expression, P transpose, what this expression is exactly saying is that X is optimal if and only if, what does this expression say? P transpose A is less than or equal to C, which is exactly saying that P is dual feasible. Let's write out the dual problem here from the previous slide. Maximize P transpose B subject to P transpose A less than or equal to C transpose, and P is free, unrestricted in sign. So we've got that, and now let's also see what the relative values are. So what is P transpose B? Well, again, I'm defining, in case I didn't make it clear by this, by writing this, I'm writing let P equal to C B transpose A B inverse. So what's P transpose B? P transpose B is equal to C B transpose A B inverse times B. Now let's group these differently. A B inverse B, well, that is just XB. So this is equal to CB transpose XB. But CB transpose XB is also equal to C transpose X, because X is 0 on all of the indices that are not B. So P transpose B is equal to C transpose X at this point. Again, which point is that? At the point where we have all of the reduced costs greater than or equal to 0. And since P transpose B is less than or equal to C transpose X for all feasible P, that's a statement of weak duality, then this means, so let me write that out, since, I guess I should have probably put hats everywhere here. Let me quickly do that. I'll call this hat, hat. I'm sorry if I've missed a few. And since for any dual feasible P and X feasible, I have P transpose B is less than or equal to C transpose X, this immediately implies that P hat and X hat must be optimal. This is so simple and algebraic and just follows from the simplex method that it's almost hard to see that basically we just use simplex method to prove strong duality. So that's it. So let me give a summary of strong duality for linear programming. So first, if an LP has an optimal solution, then so does its dual. And optimal values are equal. Also, we know even just by weak duality that if the primal is unbounded, that means that minimization problem has a direction which can take us to minus infinity. Well, there's no possible way that there is any feasible solution to the dual, because we know that all of the values C transpose X is always greater than or equal to any feasible value. P transpose B for any feasible P. So if the primal is unbounded, then it must mean that the dual, that's a proof that the dual is infeasible. And the symmetric holds as well, because the dual of the dual is the primal. Another extremely important thing that we've seen, and we're going to use repeatedly, is that the simplex algorithm reveals the primal and dual optimal solution. Reveals the primal and dual optimal solution. Namely, we get X, and we saw this from the original simplex, is AB inverse B and 0, but also the optimal solution P is equal to CB transpose AB inverse. Inverse. So another way to think about this is that we can always look at the reduced costs. And we've always got this sitting up there. So we always have the reduced cost. So there is always a basic feasible solution that we're always trying to improve. And then how do we interpret CB transpose AB inverse? That's sitting in the 0th row. Well, until we're optimal, so until we reach optimality, namely, until C bar, the reduced cost, are greater than or equal to 0, then what can we say about P transpose, which is equal to CB transpose AB inverse? Well, it is infeasible. It's dual infeasible. So what we're seeing is that simplex algorithm is in fact operating both on the primal and the dual, and it's constantly trying to make the primal optimal, and it's trying to make this dual variable feasible. So this is a key point, and we're going to come back to this. We're going to come back to this a number of times. Last important point that we need to talk about is this property called complementary slackness. And the key theorem says the following. Let's take X and P, a primal feasible and dual feasible pair. So let's let X and P be a primal feasible dual feasible pair. I'm not saying that they came from Simplex method or whatever. I'm just saying they came from their primal feasible, dual feasible. Then this pair XP is primal dual optimal if and only if. Well, we already know one condition. We know a condition that says that they're primal dual optimal if they're both feasible if C transpose X is equal to P transpose B. So we already know that by just by virtue of weak duality, in fact. But this is an if and only if condition that is going to be critical for the development of the primal dual algorithm, which is going to occupy us for a large part of this of this course. And it says that another characterizing condition, an if and only if condition for optimality, is that they're optimal if and only if, I'm going to define variables ui, which is equal to pi times ai transpose x minus bi, if this is equal to 0 for every I, and vi, which is cj minus p transpose aj times xj equals 0 for all j. So before we prove this, let's just appreciate what it's saying. It's saying something very intuitive and very appealing from a resource or economic interpretation of linear programs. It's saying that, and this is exactly why dual variables are often thought about as prices or the marginal cost of a particular resource. So if you have a1x less than b, b is the amount of resource that you have, and basically what is and its dual variable would say be p. And what is this first constraint saying? It's saying that if ax is strictly less than b in the optimal solution, in other words, if ax minus b is not equal to 0, it means p has to be equal to 0. So for the economic interpretation is that if in your optimal solution you are not using all of a particular resource, it means the marginal value of that resource to you is 0. That statement by itself is clear. If someone offers to give you, to change nothing else but give you an epsilon amount more of a resource that you already have some left over in your optimal solution, then it means that that's on the margin, not worth anything to you. What's interesting about the statement is that it is an immediate consequence of duality, and it's borne out by the primal and dual solution. So and similarly in the dual. Okay, so the dual constraint Cj minus P transpose Aj times Xj, this is equal to 0, and this holds whether or not we are in standard form for a linear program. Because for standard form, we know that A transpose X is always equal to Bi. Okay, but now let's see the proof of this important relationship. Okay, so first of all, Ui and Vj are always greater than or equal to 0 for any I and j. So you should go back to see where did this come from, and why is it that this is always the case? I mean, basically, the answer comes from feasibility. That we're insisting that P is dual feasible and X is primal feasible. Those two together imply that ui and vj are non-negative. So if ui is non-negative, then and vj is non-negative, then if I look at the sum of ui plus the sum of vj, it's enough for me to show that the sum is equal to 0. Because if I'm summing non-negative things, the only way that the sum can be equal to 0 is if each individual one is equal to 0. And now just writing out the relationship, you see that this is equal to the sum over I of pi ai transpose x minus the sum of pi bi, which I'll just abbreviate by p transpose b, plus the sum over vj. So the sum over vj is going to give me the sum of cj xj, which is just c transpose x, minus the sum over j of p transpose aj xj. But you can see that this is equal to p transpose ax minus p transpose b plus c transpose x minus p transpose ax. Those cancel. So this is equal to c transpose x minus p transpose b. So what does this tell us? The conclusion here is that ui equals vj equals 0 for all ij if and only if there's no duality yet. If and only if c transpose x equals p transpose b, which was our original condition for optimality for the primal dual feasible pair. So in other words, if and only if x and p are in fact optimal. So this is the proof of complementary slackness. It's an important property which we're going to be making really great use of in future lectures. We're going to stop now and continue next time with in the next lecture with duality of the simplex method.